Okay, good afternoon, everyone. My name is Philip Jeremic, and today we're going to be talking about a first failure data capture mechanism called the JitDump. All right, so what is JitDump? Well, as developers working on the JIT compiler within OpenJ9, we all have to debug problems, either from test failures or during development. Some, if not most of these failures we encounter are actually intermittent. We want to ensure that we have enough information to debug JIT-related issues when they first occur. And one of the most important tools for debugging such issues are the JIT trace logs. So JitDump is a reactive mechanism for obtaining JIT trace logs after a problem happens. And that happens within the same JVM that's actually executing and that caused the problem in the first place. So JitDump is not something that's new. The technology has actually been around for about a decade now. And some of us have a firsthand notion of the JitDump actually not being too useful. And most of us don't even bother looking at it. How often, for example, have you had a problem that you were looking at and a JitDump was generated and you glance over at the file size and you realize it's basically empty, so 100 or so bytes in this case. You open up the file and it says something prevented us from generating the JIT trace log. And it's quite unfortunate when this happens. Or, for example, how often have you had a JitDump being generated and you open up the file and you take a look at what's inside and you realize, again, some problem happened and we only have a partial log to look at. So I personally have encountered many of these issues myself, and I thought, how much more efficient we would be as a team if we just had these trace logs available to us always. And that brings us to some of the goals for today. I think above all else, I wish to eliminate some past stigma about JitDumps not being useful and have developers look at JitDumps as one of their first steps within a defect investigation. I wish to promote and encourage the use of JitDumps to debug JIT problems from here onwards. And from this presentation specifically, I hope to teach you a little bit about compilation control and how the JitDumps are generated. And hopefully we'll do a demo later on. And finally, last thing I want from this presentation is to spark some interest into any other ways that you can think of to make us more efficient as a team. I personally believe that if we can save, for example, even 10 minutes of a developer's time on a particular task, this can scale across all developers indefinitely, and it's a huge overall win for efficiency for our entire team. So without further ado, I introduce you to the JitDump of the future. So over the last several months, we've been working to improve the JitDump mechanism so that we can guarantee that a JitDump will be generated for all JIT-related failures. So that means if you have a failure within a JIT method, I can almost guarantee you that there will be a JitDump and it'll contain a trace of that particular method. The JitDump mechanism can handle both crashes in application threads and compilation threads. And it now attempts to use the same options as the original crash compile for the recompilation. And this is kind of a best effort for application threads. And we'll see some examples of this later on. If, for example, you have a failure that crashed during inlining, we will enable trace inlining in our trace logs to give the developer maximum amount of information to hopefully be able to diagnose the problem right when the problem first occurred. And we have some new features, which I'll highlight later, a ton of bug fixes and general improvements to the mechanism. But to understand how the JIT process works, we first have to understand a little bit about compilation control. So we can think of JIT compilation as an investment into the future performance of the JVM. And the compilation control logic is kind of the investment portfolio manager in this case. So in a dynamic environment such as the JVM, JIT compiling methods comes at a cost, since there's a trade-off to be made in terms of execution resources. The JIT compilation happens on the same system, which is running the application. So JIT compilation is competing with resources that could otherwise be spent executing the application in the interpreter. And because of this trade-off, compilation logic is very important for performance of the JVM. The logic decides which method to compile. Say, for example, a method executes only 10 times during the lifetime of the JVM. Do we think compiling that method might be beneficial? Probably not, right? But what if a method gets executed 1,000,000 times? Chances are compiling that method is typically going to be a net positive in terms of performance. So in that case, the answer is yes, we do want to compile that method. So at what point does our answer change from no to yes? Well, compilation control logic is what decides that answer. It also decides when to compile. Compiling methods too early may give us a short-term gain, but at a cost of lower overall performance later on, as we haven't really collected enough information about the execution of a method to be able to make good compiling decisions. For example, interpreter will collect branch bias information and profiling information, which the JIT will later consume to optimize the hottest parts of a method. If such information is unavailable or lacking, we will not be able to make good decisions while compiling. So compiling too early is not as good. Compiling too late, and we've missed out on too much performance. And the last thing compilation control does is it answers how much resources we want to invest in compiling. We have, of course, different compilation levels and multiple compilation threads running. So which compilation thread gets to compile which method, at what optimization level, etc., is some of the things that the compilation control logic will answer. So as you can imagine, there's no really right answer to any of the above questions. And which is why compilation control typically has quite a lot of heuristics, which have been fine-tuned over decades of JVM development. And this is also partly the reason why it's quite a big source of non-determinism. Compiling the same application many times can result in slightly different JIT compilations happening to the exact same method. So what happens when we have a bug in either within the JIT compiler itself or in the generated JIT method binary? Well, more often than not, we get a Heisenbug. So a Heisenbug is a class of software bugs that seem to kind of disappear or alter their behavior when we attempt to study them. For us JIT developers, what this means is, like grew in the picture, you find out a problem, for example, a crash in the JIT library. We attempt to reproduce the problem and it just stops happening. I'm sure many of you have, or if not all of you have encountered this. So because of these timing differences, even such a simple thing as logging trace messages to a file can introduce enough change into the system to prevent us from being able to reproduce issues. So just to give you a few examples, a method compiled early during startup of the JVM can be very hard to trace because file IO can delay the method compilation just enough so that it pushes the method outside of the startup phase, and suddenly the compilation control logic will make a whole bunch of different decisions on how we should compile this particular method. Other things are, for example, block frequencies or profiling information might be different from run to run depending on when the compilation was triggered. And kind of the sum of all of these things, and there are many more, are kind of the non-deterministic factors that can make reproducing problems in the JIT compiler quite difficult. So a question you might ask yourself is, why do we need to reproduce the original problem in the first place? Well, while we can debug some issues through system core dumps, that will typically only tell us why the observed problem or why the observed crash happened. But it won't really tell us how we got there. What we really need is a system core dump and often a JIT compilation trace log in combination from the same JVM to be able to determine both the why and the how. And that's typically all that we need to be able to solve JIT bugs. So how do we typically solve these Heisenbugs? Well, we use grinders, of course. Not the grinders that are depicted here, but Jenkins grinders. So I'm not sure who actually came up with this term, probably predates me, but grinders is just a word that we use to run a test many, many times with user-defined options. We see examples of these in various OpenJ9 issues where people will post links to Grinder pages on Jenkins, and they just literally put a test within a for loop and just run it many, many times, and we report the failure rate of the issues. Depending on the failure rate, we choose different debugging techniques, but often from the system core dump, we can identify why a JIT bug occurred, and usually within which method. And then we, of course, kick off grinders to try to get a JIT trace log. However, this is just an incredible waste of resources. If we have, for example, a problem that reproduces 1 out of 100 times on a 5-minute job, it'll actually take 8 hours of machine time to run that grinder. Of course, we do it in parallel now. And it can usually take multiple of these grinders to get an actual JIT trace log to be able to do some debugging. So it's an incredible waste of machine resources, which could otherwise be spent elsewhere. But when in doubt, we brute force, right? So one of the other issues with grinders is they're not typically available to end users. This is kind of something we use as developers to debug tests, but end users don't have the luxury of running their test many times, or using grinders, or even have a defined test to run. So we typically encounter this in service or servicing the JVM. We don't have the liberty to use grinders to obtain JIT trace logs, so our problem becomes much, much more difficult. So there must be a better way, right? Well, there is. The mechanism is called JitDump, and like I said before, it's a first failure data capture mechanism. It's a dump agent, which is part of the JVM and can be configured via other xdump options that you typically see for Java cores and system cores. The mechanism is implemented with POSIX signal handlers, and which is provided to us by the ORMAR port library. And what the JitDump mechanism does is when we detect a failure that could be related to a JIT bug, we go ahead and recompile that method and generate JIT tracing information and dump that onto the disk. And the type of tracing information that we can obtain depends on where the problem occurred. So it can handle both compilation and application thread bugs. And we'll see this in a demo shortly. The mechanism itself is generated by default for any fatal problem that results in us bringing down the entire JVM. So this is typically signals that can't be handled or that don't get handled, like segmentation faults, bus errors, or traps, or things like that. It can be disabled via an option and is fully customizable with the standard xdump options and events. The agent is supported on all OpenJ9 platforms and all operating systems, and some of the new JitDump features and improvements that we've put in are available in release 0.26, which is coming out next month. So what are these new features that I'm talking about? Okay, so let's take a look at an example right here, a simple example that we'll walk through and kind of understand what this new JitDump agent sub-option does. So we have a test fib method here. Let's pretend we're in some test bucket and we're calling our own function, which we wrote, compute Fibonacci. And we're trying to get the 7th Fibonacci number. The result we expect is 13, and then we're going to assert that that value is correct, right? Pretty simple test. So let's pretend that this compute Fibonacci method call computes the wrong result. It doesn't actually crash. It doesn't throw an exception. It just computes the wrong value, right? Which means that our assert equals JUnit assertion is going to throw an assertion error. And that's going to percolate through the stack and eventually be reported to the user. Now, it's important to note that this method, which computed the wrong result, is not going to be on the backtrace, on the stack backtrace of this assertion error that gets thrown. So what are the ways that we as JIT developers might debug this problem? Well, first thing is probably we're going to try to get a trace log of compute Fibonacci and see what's going on inside. But you try to get a trace log and you encounter a Heisenbug. The problem just stops reproducing. So that's a no-go. Okay, let's throw this thing in a grinder. The problem with grinders is the reproduction rate might be low, and for every successful pass of the grinder, you're going to be generating a JIT trace log if you use the xJIT option. And the problem, of course, might not even reproduce in a grinder. And another problem is that, okay, maybe we can use an xdump option to generate a system core when this assertion error gets thrown. Okay, we can do that, but the problem is our bad method is nowhere to be found on the backtrace of this assertion. So that kind of won't help us to determine why the problem happened, because this method was executed after the assertion or before the assertion was thrown. So how do we typically fix these problems? Well, we can use a new JitDump feature. It's called a sub option called opt equals, and we can configure JitDump to on an event. So when we have a throw event, we can filter it to a specific exception, for example, the assertion error. And whenever an assertion error gets thrown in this particular method, testFib, 3 stack frames below, because it's assert.equals that's throwing the error, we're going to generate a JIT trace log of this particular method that we specified. And we can specify a full method signature. So in this case, it's test arithmetic compute Fibonacci. So when this assertion error gets thrown, the JitDump mechanism will actually recompile this method so we get a JIT trace log for it. And remember, this is a reactive mechanism. So that means that we only get a JitDump when we actually have a problem. And typically, when we do these recompilations, they look nearly identical as the original compilation. So from that, we'll be hopefully able to determine why the problem happened. Okay, so take a small breather. Let's go into a little demo where I have 3 different scenarios on JitDump that we'll go through in a terminal. Okay, so first one is a crash in a compilation thread. There's a couple of things that changed in the JitDump logging and the actual trace files. So I'm just going to go through 3 different scenarios where a JitDump gets generated and how it looks and what kind of information you should be looking for. So this is a crash in a compilation thread. We're just running java-version. We run it and hopefully we'll crash, and we do. Okay, so there's a whole bunch of information. The problem is still running, and now it's complete. So I'm going to scroll up a tiny bit and we're going to check out what happened. So it's telling us there is an illegal instruction and it gives us a VM state. Okay, that's interesting. The next thing we take a look at is the module. It's telling us that this crash actually happened in the JIT module. So this means it's a compilation thread crash. And we actually print the symbol that crashed. So to a trained eye, J9 estimate code size, this would be an inliner bug, but we can also confirm that via the VM state. So let's find out where we actually crashed. So if we run java-xjit and we put in a colon, we print out the VM state. It is telling us we crashed during inlining. So the VM state is telling us this is an inliner problem. Okay, let's see what else happened. So there was a dump event. It's a general purpose fault, which makes sense because it was an illegal instruction. The system started generating a core dump. That's not kind of interesting to us. And later on, the JVM requested that a JitDump be generated. This is great, right? So we have a JitDump being outputted here. Some things that are new, we actually print out what thread we actually crashed in. So in this case, the JitDump is telling us we crashed in compilation thread 0. And this is the address of the VM thread which we crashed in. The JitDump is telling us it is tracing the IL of the method that crashed, and it's requeuing the recompilation of that particular method. The next line tells us that the JitDump had a recursive crash occur on the diagnostic thread. And we'll see what this means later, but basically we queued the method in which we crashed for recompilation, and that recompilation itself crashed, which is great. That means we are tracing the method while it crashed, and we're going to have the full trace log of the method within our JitDump. And finally, the JitDump has ended. So if we take a look at our disk, we can see the JitDump has been generated. It is definitely non-empty, and we can open it up. Okay, so within the JitDump now looks exactly like a typical trace log would. The first thing that we see is the IL of the actual crash thread. So this is just the IL that we pull from the original crash. Okay, and this is not too useful in this case because we crashed somewhere during inlining, but it'll tell us what the original trees were at the point of the crash. Okay, so we search this down, and now we found that after we traced the IL of the crash thread, we queued a recompilation of the exact same method. And we know from our VM state that we crashed during inlining, so we can search for main equals inlining. And here's the inlining optimization. And right here, you can see that we actually enabled trace inlining for this compilation. So this is some trace inlining calls, and eventually, shortly after, we crash. Okay, the JitDump has been fully generated, and hopefully the trace inlining diagnostics should be able to tell us all that we need to be able to determine the cause of this problem. Okay, so that's a crash in a compilation thread. Let's see what happens for application thread crashes. So we have a crash in an application thread. This is just some crash that I put into the JDK for purposes of illustration. So again, we're running java-version. We're going to run this, and hopefully we'll see a crash. Okay, so we have another crash. Systems processing looks like a core dump. And then eventually the JitDump mechanism triggers. Okay, so again, we can take a look at all of our information. VM state in this case is typically going to be 0 because we have an application thread crash. It tells us which compile method we crashed in. In this case, it's class.getPackageName. And later on, the JitDump mechanism was triggered. It's telling us the event occurred on the main thread. So this is an application thread. And then it started recompiling every single method that we saw on the backtrace. So if we open up, so we have class, get package name, we have module path, exploded packages, etc. So we did generate a Java core in this case. So we can just take a quick peek at the Java core. We can go down to the current thread section, and we can see the entire backtrace had all of these methods on there, and all of these methods were JIT compiled. So when the JitDump mechanism triggered, we walked back to stack, and any JIT method that we encountered on the backtrace, we queued for recompilation. So this is what the messages above here tell us. So it's recompiling a whole bunch of methods. And naturally, because we have so many methods compiled, our JitDump is going to be quite large. So if we open that up, hopefully we should see a whole bunch of recompilations. And hopefully the bug, since we crashed in get package name, hopefully the bug will be somewhere on the backtrace of this particular example. So we have one recompilation here. Just going to copy that line, and we can search for it. So here's our first recompilation. So let's get package name. Search downwards. Our next one is module path, exploded packages, and we can keep searching. So all of these methods got JIT compiled. And at the end, we can see that our JitDump is completely finished. Cool, right? All right, and the last example I want to take a look at is an example in which a JitDump won't be generated. So I have an example called example. And if I run it, we'll actually get an array index out of bounds exception. And I crafted just a simple example here. Take a look at what it looks like. So it's just the main function or the main method. It allocates an integer array of length 2. And then in a for loop, 1,000,000 times, it calls this get value at index. It passes in the array and the integer 1. And all this method does is it just literally returns an array index. Right? It's pretty simple. So if I run this with the interpreter, so I put xint, I observe that the problem actually doesn't happen, which is quite interesting, right? So it's very likely a JIT bug. So if I turn on the JIT, xJIT, suddenly the problem starts happening, right? So we have a JIT bug somewhere, but we have an exception thrown and a JitDump is not generated. So how can we use the JitDump mechanism to actually generate a trace log of this method? Well, as with the example previously, we can use some xdump options. So we can specify something like xdump. We can do an event. First of all, we can specify we want a JitDump, and we'll do an event when an exception gets thrown. That'll hopefully generate a whole bunch of JIT trace logs. So let's just run that, for example. Oops. I have not specified something correctly. I might have to look up my previous example here.
You might need to use events.
Yeah, I must have misspelled something. All right, so here's what we just executed. So xdump Jit events, right? I put event instead of events. Thank you, whoever said that. So this has actually not reproduced our issue. And you'll notice that we started generating a whole bunch of JitDumps for every single time a throw event got thrown. And these are class not found exceptions. But at the very end, you'll notice that we actually didn't reproduce the bug. So what can we do? Well, we can use a filter, right? We can say filter equals, and we go up and we can copy our exception. So in this case, it was an array index out of bounds exception. You can use a wildcard character and say, please only generate a JitDump when an exception is thrown and only when array index out of bounds exceptions are thrown. And if I run that again, you'll actually see that the JitDump was triggered. The reason why it was triggered is it's in response to an event. The event was a throw and an array index out of bound exception was thrown. The event occurred in the main thread and it's recompiling our example get value at index method. Okay, so that's our JitDump. If we take a peek inside and take a look at the IL, we see that there's actually 2 bound checks. So I just hacked the JIT to insert an extra bound check to always bound check against index 2. And of course, our array is of length 2. So this is going to be an array index out of bounds every time it executes. So this is just a kind of a hacked up example I put into the JIT just to illustrate how we can use the JitDump to generate these logs. Okay, that's it. That's our last example. Now, let's go back to the example of an application or a compilation thread crash. So what I want to do now is kind of go through the process that the JitDump takes through the JVM and what happens in the compilation threads. So you kind of get an idea of how the JitDump mechanism works and how it's able to generate these trace files and turn on all these options. So in this scenario, we have a JVM with 2 application threads, app thread 1 and 2, and we have 2 compilation threads in this case. One of which is in a suspended state. By default, there's always at least one active JIT compilation thread, which is just spinning around waiting for work. As application threads execute different methods, we decrement the counts, and once the count reaches 0, we queue a method for compilation. Now, this happens asynchronously, meaning that when we request that a method be queued for compilation, we don't actually block the application threads. They continue executing while the JIT compilation threads take care of the compilation request in the background. So application thread 1 keeps executing, and compilation thread 1 sees that there's an entry on the compilation queue, and it starts processing that entry. Now, one of the very first things that a compilation thread do is it'll check what the compilation queue looks like. So remember, as these application threads on the left are executing, they're executing methods all the time. Method counts are getting decremented, and they are queuing more and more compiles on the compilation queue. Now, compilation thread 1 takes a look at the queue and asks itself a question. Hey, given the queue size and the number of compilation threads I have active right now, do I need help? Am I able to process most of this queue by myself, or should we activate more compilation threads? So in this case, let's pretend that there was so many methods on the queue that this compilation thread says, okay, I need help. Let me activate another compilation thread. So it sends a wake up signal to another compilation thread, in this case, thread 2. And this signal is also asynchronous, meaning that we're just going to keep on moving. We're going to start processing entries. We don't care when the other thread wakes up. So compilation thread 1 picks up an entry off the queue and starts to compile. Meanwhile, at some point, compilation thread 2 has woken up and it starts processing entries off the compilation queue itself. It also asks the question, hey, given the queue size, we have 2 compilation threads active now. Do I need more help? And the answer was no in this case. So it starts to compile methods on the queue itself. Now, the application threads are executing, queuing compiles all the time, but they're kind of not interesting to us for the purposes of this investigation. So we're just going to collapse them so we have more room to work with. Okay, so at some point, compilation thread 1 has completed the compile of whatever method it picked up off the queue, and it starts processing another entry off the queue. But compilation thread 2 has actually crashed somewhere during the compilation of whatever method it picked up. And we'll call this the original crash, and we'll see why in a moment. We need to be able to distinguish between the original crash and the recompiled crash, as we saw in our demo previously. So we're going to collapse compilation thread 1. It's going to continue processing the queue, but that's not really too interesting to us. Let's see what happens on the second compilation thread once we encounter the crash. So when I say crash, I typically mean a POSIX signal which was not handled. These signals, examples are, for example, a segmentation fault, a trap, an illegal instruction, etc. But this is something that happens on a compilation thread. For crashes on an application thread, something different happens. So let's take a moment to understand what happens for when signals get raised in an application thread, similar to compilation threads. So for example, a typical example of this is dereferencing null. And dereferencing null in Java does not necessarily imply that we're going to get a segmentation fault within the JVM. And the reason for this is that during startup, the JVM registers a stack of signal handlers, which can handle various POSIX signals. Each of these signal handlers is given an opportunity to handle a signal. And in this case, in the case of an application thread dereferencing null, the JIT signal handler will be given an opportunity to handle it. And here's a really, really dumbed down view of what the JIT signal handler might look like. So we first check if it's a segmentation fault. And if it is, we know the address at which that segmentation fault occurred. So we try to see if there is a JIT method at that address. So we try to find the metadata corresponding to a particular PC. If there was a JIT method at that particular address, we actually get, we try to find the piece of code which is able to throw a null pointer exception for that JIT method. And we update the actual PC value with that location. And then the JIT signal handler says that the exception was handled and please go to the PC that I specified. So what this in effect does, if, for example, we dereference null in a JIT compiled method, we will actually throw a null pointer exception rather than crashing the JVM. But if, for example, this segmentation fault didn't occur in any JIT method, the JIT signal handler would just say, oh, please continue to search. Perhaps another signal handler is able to handle this particular signal. Okay, so that was kind of a sidetrack to see what happens on application threads. But remember, we crashed in a compilation thread. So the same logic happened. This signal passed through this JIT signal handler because the location in which we crashed was not associated with any JIT method. And at the very end, once all the signals handlers have had a chance to handle a particular exception, there is a catch-all signal handler at the very end called the dump agent signal handler. And this signal handler is responsible for just generating diagnostic information about the JVM. So hopefully a JVM developer will have a chance to investigate the problem and determine the cause. Okay, so the first thing the dump handler does is it produces a bunch of dump files. So the typical dump files that you see is Java cores, system dumps, snap traces, etc. And one of those dump agent that runs is actually the JitDump. So the first thing the JitDump agent does is it dumps the IL of this particular crashed method. And then it requeues it, it wakes up the diagnostic thread. So this is just another thread which was previously in a suspended state. So we send an asynchronous signal to wake this thread up, and this thread is going to begin waiting for work. And then the JitDump mechanism queues a synchronous compile. Remember, application threads queue asynchronous compiles. The JitDump mechanism queues a synchronous compile, which means this compilation thread is not going to block, waiting for this compile to finish. Okay, so this diagnostic thread is just waiting for work. Eventually, once this queued compile is queued, the diagnostic thread has the ability to pick up that compile. So it starts processing the entry. And the way it compiles is actually within a protected compilation unit. So what we do here is that we actually register a signal handler for this compile, and it's a custom signal handler within the JitDump mechanism itself. We call it the JitDump signal handler. And what this does is if we encounter a crash within this protected compile, this signal handler will get a chance to handle that exception. And what we do here is within this signal handler, we just say, hey, a recursive crash occurred. We're going to print that out to the std error, and we're just going to return that, yes, I handled the signal. And this is what was output in our demo example. So in this case, we reproduce the original crash. So remember, this was the original crash in the compilation thread. And on the right-hand side, we have a reproduced crash within a recompilation. But except now, in this case, we have tracing for that particular crash. So the diagnostic thread was able to handle, quote unquote, this crash by doing nothing, just printing to std error. And the last thing it does is it signals that the compilation has been complete for anyone that's waiting. This signals compilation thread 2, which was waiting for that synchronous compile to finish. So this thread gets unblocked. The diagnostic thread is waiting for more work in case the JitDump mechanism wishes to queue more compiles for it to recompile. But in this case, it doesn't, because the only compilation of interest for a compilation thread crash is the actual method that we crashed while we were compiling. So this thread gets unblocked, and eventually we end up calling abort, and this is what terminates the JVM eventually. So quite a lot of information. A little summary of what we learned. Compilations, which are queued by the crash thread, happen on a separate thread called the diagnostic thread. This diagnostic thread is always suspended until it's woken up by the JitDump process. And the JitDump process will suspend the diagnostic thread when it is finished generating the JitDump. The JitDump file contains traced recompilations of the relevant JIT methods that we found. For compilation thread crashes, this is the IL of the crash thread and the recompilation of the method that crashed. And for application thread crashes, it's a recompilation of all JIT methods that we found on the stack. So before we wrap up, I want to put out a call for action to hopefully help us improve the JitDump feature. So if you are working on a defect or an end user problem and you find that a JitDump is missing or not giving you the information that you wanted, ask that you please reach out to me, and I will be glad to help take a look and hopefully improve the tool. I think as we start to fill in these gaps, the JitDump becomes more and more useful, and hopefully we can spend less time fixing defects and more time developing features. And that's it for today. Thanks so much for investing the time to listen, and we'll open the floor up to any questions that you may have.
Hey, Philip, great presentation. So I was distracted in the middle part of it, so maybe you talked about this and I missed it, but I was just wondering if there has been any thought towards a kind of programmatic interface to the JitDump thing that might help, like when you're constructing tests, if you kind of know the likely place where a problem might show up, you might be able to like seed the JIT method that would be traced on a JitDump or something like that.
I think that's definitely doable. The mechanism itself is just a static method that can be invoked. Yeah, I think that's definitely doable.
Okay, I was just curious.
Yeah, anecdotally, I think while I was working on this, oftentimes I'd pop into issues on OpenJ9 and just check, did the JitDump get generated? And I'd be often pointing out to people that, hey, you have a JitDump available, take a look at it. So hopefully, I think my biggest takeaway from this presentation, if you can take a look at the JitDump whenever you're working on a defect and just take a look at if it's there, if it's useful. And if not, please just by all means, ping me, Slack, on an issue, anywhere.
I have a question about the new options that was added to XDump for like ops for the JitDump. Is it going to be specifying only method, or we can specify a specific trace option or anything to that method?
So for now, we actually require a full method signature. And this was a technical limitation. But you're actually the second person that requested that different trace options be added. So I'm going to look into adding an option to enable that.
Okay, thank you.
I think it's also worth mentioning that as part of this JitDump process, we actually simplified all of our tracing options. I think for Cogen, all we have is trace CG and trace RA now. And for the optimizer, I think they're all controlled via, I think we merged a whole bunch of tracing options to make the JitDump mechanism be able to trace the particular optimization when we crash in that optimization. So I think the tracing has been made more robust with this change.
Any other questions for Philip? Okay, great talk, Philip. Making this feature very useful for problem diagnosis. So let's all hope for bugs now.
Thanks, Daryl.
Okay. Thanks, everyone.